So now that we've talked about how the common fork join pool works and how it's mapped and so on and so forth, let's talk about how you can configure the common fork join pool to set the degree of parallelism that it's going to provide. And again, this is going to be sort of a quick overview. We'll talk about the details when we talk more about the common fork join pool later in the course. Okay, so let's talk about this. By default, the common fork join pool has one less thread than the total number of cores that the Java execution environment knows about. And the way it knows about that, there's a method that will give the number of cores that the virtual machine or the execution environment thinks that it has based on the hardware configuration. So there's a method called getCommonForkJoin parallelism. And if you look at getCommonForkJoin parallelism in the fork join pool, it's a static method. On my quad-core processor, which is hyper-threaded, so it's got two logical cores for each physical core, getCommonForkJoin pool parallelism, or getCommonPool parallelism, returns 7. So obviously, the underlying system thinks I have 8 cores, even though I have 4. But they're hyper-threaded, so it thinks that they're 8. And so it returns 7. The reason it returns 1 less than the total number, the reason why there's 1 less thread in the common fork join pool, is because whichever thread is used to run the processing on the stream, which is a parallel stream in this case, whoever ends up invoking the terminal operation, that thread will be counted as one of the threads in the pool of threads that are used to process things. So it's the calling thread plus the pool threads. So the total number of threads will be equal to the total number of cores by default. Got it? So the question is, what if there's other things going on in the background, and which could be many things, listening to music or doing email or running some kind of query optimization for a database query, those things won't be known by the common fork join pool. That would be, of course, known by the underlying hardware, but wouldn't be known by the common fork join pool. But we'll see an example here. So it might be the case that you might be doing some background work, and you're like, I really want that background work to have some amount of the processing. I don't want to have to time slice that in with all the fork join pool threads. So what we're about to talk about, where you can either expand or contract the number of threads in the common fork join pool, is very important to get better control over total computational resources on your system. And I'll talk more about that. Sometimes you want your parallel streams to be the most important thing that's going on. Other times you want to make sure that they share everything else in a nice, convenient way. But by default, the common fork join pool will have 1 less than the total number of cores that the execution environment knows about, plus whatever the calling thread, like the main thread, happens to be. Now, here's the thing. The number of threads in the fork join pool may be inadequate. And it could either be inadequate because you don't have enough, or it could be inadequate because you have too many. The too many case might be you want to devote some cores to running Spotify. So you want really good responsiveness for your downloading and music listening. But you might not. So in any case, I'm going to look at the case here where we're more concerned about having too few threads in the fork join pool rather than too many. But the same concepts work in both ways. So here's an example of where you might have things that are inadequate, insufficient, probably a better word. So if you've got blocking operations in your stream. Now, we've talked about this before. We're going to talk about it in much more detail when we talk about some of the thread pooling mechanisms in the common fork join pool later. But imagine we have the following scenario. We've got a situation where we have a bunch of images we want to download. Let's say we have 10 images, and we've only got 4 cores or 8 cores or whatever. Let's say we have 4 cores just to make it interesting. So if we have a lot more things to download that might block, then we have cores available to, threads available to process them. We're going to end up with one of 2 problems. We're either going to end up with underutilization, where the amount of downloading we do per unit time is less than it could have been, which might be bad if our goal is to try to maximize performance. Or we could even end up with deadlock if we have recursive callbacks in our processing. Let's ignore the deadlock thing for the moment. Let's just focus on underutilization. So what will happen here if we've got, say, 10 images to download, but only 4 threads to download them in, as soon as we start downloading the first 4 images, those images will block, and because images could be large, they may block for a substantial period of time. And while those images are downloading and blocking the threads, if we only have 4 threads but 10 images, those threads are just going to wait there, and the CPU will be wildly underutilized. Because we could actually have other threads downloading the other images and then blocking in parallel. But if we only have a limited number of threads, we're not going to be able to get any benefit from having the multi-core processor. Keep in mind, when threads are blocked and there's no way to have more threads, then those cores are idle unnecessarily. Any questions about that? It's a really important point to understand in parallel processing. If something is blocked on I/O, then if a thread is blocked on I/O and there are no more threads available, then that core is effectively not being used. But if there are more threads, then when one thread is blocked on I/O, rather than having that core just sit idly by, the core could say, oh, that thread's blocked on I/O. Great, I'll put it to sleep, and I'll go pick another thread from the available threads and let that one start to run now. And then it would go ahead and run in parallel. So it turns out that blocking with a limited number of threads can be an impediment and can degrade performance. Very important concept to get your head around. Okay, so what are we going to do? Well, there's a couple of things we could do. One thing you can do, which is a little bit kind of like a sledgehammer approach, but it does work, is you can actually set the number of threads that you want to have in the common ForkJoin pool. So you can actually give it a value. You can say, I want to have 10 threads in the common ForkJoin pool. And then you can set a system property, which is a bit of a mouthful, java.util.concurrent.forkjoinpool.common.parallelism. That's a property that's defined. And you can set that property, and then that will go ahead and expand the underlying pool of threads for the common ForkJoin pool to equal whatever number you gave there. So if you know you've got 10 images at a time to download, and you're not worried about any other side effects, one thing you can do is just set that value to be the right value. The problem here is that setting that property affects all parallel streams that are available in a given process or that are capable of running in a given process. It's a process-wide value. And the reason why it's a process-wide value is because it's the common ForkJoin pool, after all. And the common ForkJoin pool, by its very nature, is common to all the parallel streams that are running within a given process. Not across other processes running on that machine, but within a given process. So what makes this tricky is, unless you know an awful lot about all the parallel streams that are in your program, setting this value has this ripple effect, hence the metaphor of the ripples, where you either have made there being way more threads than you need for other stuff, or if you set it too small, there are lots of other threads that could have run, but now you've restricted the number to just 10, or just n, wherever n is a fixed number that's set globally within a process. And it's hard to know what that value should be. For that reason, there's another mechanism, which we will talk about in more detail when we talk about ForkJoin pool, common ForkJoin pool, called the managed blocker interface. And the managed blocker interface is this cool mechanism that can be used to temporarily instruct the common ForkJoin pool to add additional worker threads if a given thread will block or may block or does block. And we'll talk more about that. It's really, really super cool, and there's some neat things you can do to program. But it'll basically expand these things. And this is very useful for behaviors that block on I/O, like our image download stuff we were just looking at, or things that will block on synchronization mechanisms, like mutexes or semaphores or something like that. And we'll talk a lot more about that later. This particular mechanism, the managed blocker, can only be used with a common ForkJoin pool, not with other kinds of ForkJoin pools, because you can have your own ForkJoin pools. And of course, this mechanism of setting the values can also only be used for the common ForkJoin pool. And we'll talk a lot more about this when we talk about the Java ForkJoin pool and the managed blocker interface. Okay, so that's the end of the discussion of how to configure the common ForkJoin pool, and you'll get some experience doing that in the programming assignments.